Assalamualaikum warahmatullahi wabarakatuh. Today, I want to present for subject BEET 3414 RF Technique and Microwave, and my class is 2 BERT S1 stroke 1. For this assignment project, we have 3 members, and my name is Muhammad Alif bin Zakaria. My metric number is B122410530, and my others member is HAFIY AHZA bin Muhammad NAZRI, B122410494, and my others member is Muhammad AKIF AIMAN bin ABDULLAH, B122410731. First of all, I want to present for introduction. Microwave passive filter are used in high frequency communication system to allow desired signal to pass while blocking unwanted frequency. They are commonly used in radar, satellite communication, wireless network, and signal processing. The insertion loss technique is used to evaluate filter performance. It measures how much signal power is lost when the filter is added to the system. Important parameters include insertion loss, return loss, stop band attenuation, and quality factor, which indicate the filter efficiency and frequency selectivity. This technique also help engineer design filter with the right balance between low signal loss and high frequency selectivity. Overall, the insertion loss method is an effective approach for designing reliable and efficient microwave passive filter. Okay, next we go to low pass filter. A low pass filter, short form is LPF, allow low frequency signals to pass while blocking high frequency signal. The cutoff frequency FC is the point where the signal start to be attenuated at 3B in the y-axis, as you can see in the diagram. And next, the frequency response consists of the pass band, transition band, and the stop band. Low pass filter are widely used in audio processing, communication system, power supplies, and image processing. As you can see in diagram, low pass filter in the y-axis you can see output in dB, and the x-axis frequency. As you can see the graph, it has filter cutoff frequency, filter order, and frequency band. And as you can see in the formula, we use FC equal to 1 over 2 pi RC. Next, we go to band pass filter. Band pass filter BPF allows signal within a specific frequency range to pass while blocking lower and higher frequency. The lower cutoff frequency and upper cutoff frequency define the filter pass band. The center frequency F0 is the frequency with the maximum response, while the bandwidth is the difference between FH upper cutoff frequency and FL lower cutoff frequency. Band pass filter are widely used in wireless communication, audio processing, medical device like ECG, and RF microwave system. And you can see at the diagram, it's same with low pass filter. X-axis frequency, y-axis output in dB. So in the diagram, it has filter cutoff frequency, filter order in dB, and frequency band. Okay, next we go to lump element filter. Lump element filter use resistor, capacitor, and inductor to control signal frequency. They are mainly used in low and medium frequency application, where component size is much smaller than the signal wavelength. This filter can be designed as low pass, high pass, and band pass, or band stop filter. Common design method include Butterworth, Chebyshev, and elliptic filter to achieve the required cutoff frequency and the filter performance. Next, we go to distributed element filter. Distributed element filter use transmission line instead of discrete R for resistor, L for inductor, and C for capacitor component. They are mainly used in high frequency application such as RF and microwave system. Filter performance depend on the length, width, characteristic impedance, and dielectric material of the transmission line. Common design method include the Richard transform and Kuroda identity to achieve the required filter performance. Okay, next we go to LAM design, low pass filter. Low pass, we get cut-off frequency FC equal to 3.4 GHz, essential loss equal to 4 dB, alliance 7 GHz, ripple equal to 3 dB, F frequency equal to 7 GHz. And for the formula, we use W equal to 2 pi F. 2 pi bracket 7 GHz for the frequency, and we calculate, we get 43.98 GHz. For WC, we use the same formula 2 pi FC, and then 2 pi FC 3.4 GHz, and we calculate, we get 21.36 GHz. And we use the formula W over WC bracket minus 1 equal to for W equal to 3.98 GHz per over 21.36 GHz bracket, and minus 1, we get 1.06. And as you can see in the graph, if we refer the graph 1.06 at 40 dB, you can see we get N equal to 4. And then for G1, if you can see for use graph, G1 equal to 3.435389, and G2 0.7483, G3 4.3471, and G4 equal to 0.5920. Okay, next we go to the LAM design low pass filter. Capacitor. Okay, we use the formula GK over R naught WC. Okay, for capacitor 1, we use G1 G1 over R naught WC. For G1, the value is 3.4389 over 15 for R naught, and WC 21.36 GHz, and we equal to 3.22 picofarad PF. For C3, we use G3 over R naught WC, G3 4.3471 over R naught 15, WC 21.36 GHz, and we calculate, we get 4.0 picofarad. And then we calculate for inductor. For inductor, we use R naught GK over WC. For inductor, inductor 2, we use R naught G2 over WC. R naught equal to 50, and G2 we got 0.7483 over 21.36 gigahertz, and we got calculate, we get 1.75 nano. And for inductor L4, we use the same formula R naught G4 over WC, R naught 15, G4 0.5920, and over 21.36 gigahertz, and we got 1.39 nano. As you can see, as you can see at the figure 10 schematic LAM low pass filter, we create the design at the software at advanced design circuit. We have a capacitor, inductor, and we use the term 191 Z equal to 50 ohm. As you can see, before this slide, we have a design. We have create design at advanced, and this is a result for low pass filter result. Output result of schematic low pass filter. So at the marking M1, in X axis, we get 3.4 frequency gigahertz in gigahertz, and for the Y axis, we marking at negative 6.795. For M2, marking 2, at X axis in frequency, we mark 7 gigahertz, and for the In dB, in y-axis frequency, we get negative 35.762.
Hi, my name is HAFIY bin Muhammad NAZRI. My metric number B1224104994. So right now we will be looking at distributed lump design theory. The main goals here is to take a theoretical lump element filter and convert it into a format that can be physically manufactured at high frequency using microwave transmission line. So the very first step in this design process is applying Richard transformation. So as you can see on the left side of the slide, you can see our low pass prototype value for a filter order of n equal to 4. This G value representing our alternating lump capacitor and inductor. G1 3.4389, which is correspond to our first capacitor. G2 equal to 0.7483 correspond to our first inductor, and G3 4.3471 for C3, G4 0.520 correspond to our final inductor L4. So because lump capacitor and inductor don't behave ideally at microwave frequency, we need to replace them with the distributed component. This is exactly what Figure 12 on the right illustrate the Richard transformation that show us how to substitute this lump element with transmission line stub of a specific line, specifically 1/8 of a wavelength lambda over 8 at the cutoff frequency. So look at the diagram A. A series inductor is replaced by a short circuit transmission line stub. The characteristic impedance of this line Z0 is set equal to the inductance. So looking at diagram B, a shunt capacitor is replaced by an open circuit transmission line stub. So here the characteristic impedance Z0 is set equal to 1 over C. So by using this equivalent distributed section, we can successfully map our n equal to 4 lump prototype into a practical microwave circuit design. Okay, now following the Richard transformation rule that we just discussed, so this next slide show how we calculate and apply the actual characteristic impedance for our transmission line layout. So on the left, you can see the calculation for our shunt component. Recall from the previous slide that for a shunt capacitor, the characteristic of impedance of transmission line stub must be equal to 1 over C. So for our capacitor, we take the inverse of G1, which give us an impedance value of 0.2908. So for the second capacitor, we taking the inverse of G3 that give us an impedance value of 0.2300. So now if we look at the figure 13 on the right, so we can see the complete physical representation of our filter using transmission line. So this diagram maps all of our calculated value into a step impedance layout. So the series section on the top represent our inductor. So you can see the characteristic impedance of this line directly match our G2 and G4 value, which are 0.7483 and 0.5920. So the shunt stub branchings of the bottom represent our capacitor. This open circuit stub use the inverted value that we just calculate, which is 0.2908 for the first stage and 0.2300 for the third stage. So this figure demonstrates the final distributed layout, translating our mathematical lump element prototype into a practical microwave transmission line design. Okay, so now that we have our initial transmission line layout, we encounter a practical problem, which is manufacturing this exactly as drawn can be difficult, especially if the stubs are too close together. So to solve this, we apply the Kuroda identity, which allow us to physically separate the element by adding redundant transmission line or unit element. So looking at the figure 14 on the left, focus on the section highlighted by the red box. To begin with the transformation, we have added a unique element, a transmission line with a normalized characteristic impedance of 1 to the front of our circuit. So this unique element will interact with our first shunt capacitor stub, which has an impedance of 0.2908. So on the right side of the slide, we perform the Kuroda transformation method on the specific section to find our new equivalent impedance value. So what do we need to do first is we identify our initial component. So the unit element is Z1 equal to 1 and the shunt stub is Z2 equal to 0.2908. So for the next, we calculate the transformation factor n power of 2 using the formula n power of 2 equal to 1 equal to 1 plus z over 2 z2 over z1. So plugging in our number, we get 1 plus 0.2908 over 1, which equal to 1.2908. So finally, we apply this n over 2 factor to find the new component value. So our new series element become z1 over n2, z1 over n power of 2, giving us 0.7747. So our new shunt element becomes Z2 over n power of 2, resulting in 0.2253. So by completing this calculation, now we can replace the original unit element and shunt stub with the new transform value. So this process not only help space out the component for manufacturing but also help convert difficult to realize series stub into more practical shunt stub across the entire filter design. Now we are taking the final mathematical step to ensure our filter can be actually fabricated. While the previous step helped space things out, series transmission line stubs are notoriously difficult to implement in planar microwave circuit like microstrip. To fix this, we apply further Kuroda identity and impedance scaling or normalizing to convert those pesky series stub into manageable shunt stub. So if you look at the design at the diagram, you will see the three sections highlighted in red. So each of these board represent a point in circuit where we are grouping a stub with a unit element and impedance of 1 to perform a transformation. We process each section individually. So right now, let's look at our example. We start by identifying our component in that section. Z1 is 0.2253 and our unit element Z2 is 1. So first we calculate our transformation factor and power of 2 using the formula, and power of 2 equal to 1 plus Z2 over Z1. Plugging in our numbers, in bracket 1 plus 1 over 0.2253, we get an n power of 2 value of 5.4385. So next we apply the factor to scale our impedance. We calculate n power of 2 times z1, which gives us a new value of 1.2253. Then we calculate n power of 2 times z2, giving us 5.4385. So as you can see in the middle and right hand calculation box, this is it. This exact same mathematical process is repeated for the other 0.7483 and 0.5920 series section. By multiplying each section component by their respective and power of 2 factor, we effectively scale the impedance and convert the entire layout into a fully shunt stub design that is ready for physical manufacturing. So now we are now entering the final stage of our filter design. So on this slide, we bring together all the transformation we have done so far and prepare the design for physical manufacturing. So in figure 16, so if you look at the top diagram, this is the complete layout of our normalized circuit after applying Kuroda identities. Notice that we have successfully eliminated all the problem series stub. Our entire filter is now composed exclusively of series transmission line. The top value like 1.2253 and 1.7483 and open circuit shunt stub. The bottom value like 5.4385 and 0.2300. However, this these are still normalized value, meaning they are scale relative to an impedance of 1. So to actually build this circuit, it need to interface with standard microwave equipment which almost universally operate at a system impedance of 50 ohms. Therefore, we must denormalize our circuit. Looking at the bottom diagram, the process is straightforward. We multiply every single normalized value from the figure 16 by our target system impedance of 50 ohm. Our unit element at the input and output, which will 1 become 50 ohm. Our first transform series line goes from 1.2253 to 61.27 ohm, and our first shunt stub goes from 5.4385 down to 271.93 ohm, and that original middle shunt stub we calculate earlier 0.2300 scale to 11.5 ohm. So the bottom schematic represent our final absolute impedance value. These are the exact characteristic impedance we will use in the next phase of design to calculate the physical width and length of the microstrip trace on our circuit board. So this slide show our initial low pass filter schematic in the simulation software right before any tuning is applied. So the setup, the S parameter block run our frequency sweep while the M sub block define the physical property of our microstrip board. The layout, we have translate our calculated theoretical impedance into an actual physical dimension, specifically width and length. So you can see the MLIN used for our series transmission line, MLOC for the open circuit shunt stub, and MTEE junction connecting everything between standard 50 ohm termination. So since this baseline layout relies purely on theoretical math, it doesn't account for real-world junction effect. Therefore, our next step is to optimize and tune this dimension to our target frequency. Following our schematic layout, this slide displays the simulated performance of the initial design before any tuning. So the graph S21, this plot shows our insertion loss S21 in dB against the frequency gigahertz. It visually demonstrates which frequency the filter allows to pass and which it blocks. So for marker 1, the cutoff, at 3.4 GHz, the signal dropped approximately negative 3.96 dB. This represents our cutoff region, showing exactly where the filter begin to heavily attenuate the signal. So for marker 2, the stop band, By the time we reach the 7.0 GHz, the signal is pushed down to nearly negative 38 dB. This indicates strong rejection of higher frequency, confirming the circuit is functioning as low-pass filter. While the filter fundamentally works, the cutoff frequency is not absolutely perfectly yet. This result confirms that translating theoretical equation into physical microstrip dimension introduce light shift, which is exactly why our final step is to tune and optimize the layout to meet our precise specification. So here we have figure 20, which display our low pass filter schematic after the optimization and tuning process. The structure remain. As you can see, the overall topology is identical to our initial design. We are still using the same configuration of series line MLIN, open stub MLOC, and T-junction MTEE. Optimized dimension, the critical differences lie in the component value. The software optimizer has fine-tuned the physically width and length parameter of our microstrip traces. This adjustment is necessary to compensate for the real-world parasitic effect at the T-junction and substrate losses that cause our initial theoretical design to miss exact frequency target. With this new optimized dimension locked in, this represents our final physical layout. The next step is to verify how this adjustment corrected our frequency response. So finally, figure 21 show the simulated output of our low pass filter after the tuning process. You can immediately see a much smoother and more defined response curve compared to our initial attempt. So at our 3.4 GHz mark, the signal is now at negative 8.19 dB. This indicates a steeper, more deliberate transition into our cutoff region. In- So the most massive improvement is in the stop band. By 7.0 GHz, the signal is attenuated all the way down to negative 71.6 dB. So recall that our untuned design only reached about negative 38 dB at this same frequency. So tuning the physical dimension nearly double our filter ability to block unwanted high frequency signal. So in conclusion, optimizing the microstrip dimension successfully compensated for real-world junction effect, resulting in a highly effective low-pass filter with excellent deep stop band performance.
Assalamualaikum and hi, my name is Muhammad AKIF AIMAN bin Abdullah. My matrix number is B1224107 and 31. So in this slide, I will explain about the calculations used to design our band pass filter. So firstly, we determine the lower and upper cutoff frequencies. Our filter has a frequency cutoff of 3.4 GHz and a bandwidth of 340 MHz. So the value of 340 MHz is we take 10% from the cutoff frequency. So then we apply it to the formula, which is F1 equal to 3.4 GHz minus 340 MHz divided by 2. So we get the 3.23 GHz of lower cutoff frequencies, and then we calculate the upper cutoff frequency, which is F2 equal to 3.4 GHz plus 340 MHz divided by 2. So the value for upper cutoff frequency is 3.57 GHz. Then we convert them into angular frequencies using the formula of omega equals to 2 pi f, which gives us the value of omega 1 is 20.295 GHz and omega 2 equals to 22.431 GHz. Then we calculate the fractional bandwidth denoted by this
triangle symbol. So the formula is omega 2 minus omega 1 divided by omega 0. So the result will be 0.1 or equal to 10% of fractional bandwidth. So next I will be explaining about the calculations for the shunt element of our bandpass filter. So first we calculate the inductor L using the formula L equals to fractional bandwidth times by R0 divided by G1 and omega 0. So by this formula, by substituting the values, we obtain L1 equals to 0.0681 nanohenry, L3 0.0538 nanohenry, and L5 0.0396 nanohenry. The used formula is the same. We just need to change the value of G. It depends on the G values that differs the value of the inductor. So next, for the capacitor equation, C equals to G1 divided by fractional bandwidth times R0 times omega 0. So by substituting all values, we get C1 equals to 32.2 picofarad, C3 equals to 40.7 picofarad. Again, the only thing that differs the value of this capacitor shunt value is the value of G. Okay, so next I will be presenting about the calculations for series elements in our band pass filter. So first we calculate the inductor using the formula of L equals to G multiplied by R0 divided by fractional bandwidth times omega 0. So after substituting each inductor using their own G values, we get L2 equals to 17.51 nanohenry, L4 equals to 13.85 nanohenry. Then we calculate the values for the capacitor. We use the formula of C equals to fractional bandwidth divided by G times R0 times omega 0. So again, substitute them into their own G values. We get C2 equals to 0.1248 picofarad and C4 equals to 0.1579 picofarad. So after we calculate the values for the shunt and series connection, we connect them into the ADS software. So this is our schematic circuit. After we place and connect all the wires of each component, we change the value of each inductor and capacitor according to our calculations earlier. After we have done the previous part, we simulate the ADS circuit. So this is the result that we will get. Then we put the marker of the frequency cutoff, which is 3.4 GHz, and the second marking will be the M2 equals to 3.23, the lower cutoff frequency that we calculated earlier, and the marking 3 will be our higher frequency cutoff that we calculated earlier, which is 3.57 GHz. So for the discussion that we have learned, we have successfully designed microwave passive filters using the insertion loss method, which Butterworth and Chebyshev approximations. Then we have achieved the required design specification of 3.4 GHz cutoff frequency using the 3 dB ripple with 40 dB insertion, loss at 7 GHz with the 4th order filter n equal to 4. And then we have designed and analyzed both lump element and distributed element filters using Richards transformation and Kuroda's identities. And then the design filters provide low signal loss, good frequency selectivity, and are suitable for RF microwave, radar, satellite, and wireless communication systems. And last one for the conclusion, we successfully designed a fourth order microwave low pass filter using the insertion loss method with a 3.4 GHz cutoff frequency, 3 dB passband ripple, and 40 dB insertion loss at 7 GHz. Then we applied Richards transformation and Kuroda's identities to develop a compact and efficient microwave filter. Then the filter provides good signal quality, low power loss, and reliable performance to RF and microwave communication systems. And the last one is future work can focus on higher order filter designs and new materials to improve performance over a wider frequency range. That is all from me. Thank you.